So, sketching the graph of a rational function, the first one in this set. Well, sketching the graph means I need to know where does it cut the axis, where are its turning points, and with rational functions, are there any asymptotes? So, just sticking to that order, I suppose. We're going to put it all down here, it's going to take a lot of room. Where does it cut the axis? Right, it cuts the y-axis if x is 0. In which case y will be negative 2 upon 1, which is just negative 2. So there's a point, 0, negative 2. X-axis, in that case, y would have to equal 0. Now if a fraction equals 0, that means its numerator should equal 0. And we're going to have this exclusion clause later on with asymptotes. So it means x minus 2 has to be 0, which means x is going to equal 2. So there's another point, 2, 0. So I've got its intersection with the axis. Next, asymptotes. Take the vertical one first. Vertical asymptote. Well, I'll get a vertical asymptote if the denominator ever equals 0. Because that's when it all starts to go awry. If I try and divide by 0, the answer just shoots off like a big smear in the graph that streaks it through to infinity. In which case, x equals negative 1. Now quite often from just the nature of the points you've got in turning points, you can snake it through. But I'll just determine what exactly happens at negative 1. Well, this function will tell me. So I'll do this at the side here. What happens as x approaches negative 1 from behind? If it sneaks up from behind, what happens to y? Well, here's the expression for y. Now, I'm only considering it in the neighbourhood of negative 1. Now, if x is negative 1, the top's going to be negative 3, no matter whether it's a little bit less than negative 1 or a little bit more than negative 1. That's not sensitive to negative 1. The top's always going to be negative. It's the bottom that's sensitive to negative 1. When it is negative 1 at 0, change it just slightly and it flips positive and negative. So if I go on the negative side of negative 1, the bottom flips negative, giving me a positive answer altogether. So that means as it approaches that, it's going to approach positive infinity. What happens as it approaches negative 1 from the positive side? Well, it'll be the same answer on top. The top's not sensitive to negative 1. Negative 1, make it slightly bigger, it's still going to be negative. It's the bottom that's sensitive. If I push it just a little bit further from negative 1, the positive will win, that term will go positive, which means that's going to go to negative infinity. If I want a little sketch of my asymptote x equals negative 1, then what's happening is this. On this side, as I approach it from behind, the answer is going to go off to infinity. And on this side, as I approach it from the front, it's going to go off down to negative infinity. So that's how we'd approach that vertical asymptote. What about a non-vertical asymptote? I'll just put asymp. Well, non-vertical asymptote. Now there's two ways you could do that. If I just wanted to know where it was, then I could do this instead. I could say, I'm going to rub this out in a minute. I could say I've got x minus 2 over x plus 1, divide everything by x, and I've got 1 minus 2 over x over 1 plus 1 over x. And if I let x tend to infinity, these fractions disappear and it leaves me with y equals 1. Y tends to 1, so I know I've got a non-vertical asymptote, a horizontal one at y equals 1. But that doesn't help a great deal with the how does it approach it business. Although quite often all the other features constrain it to approach it in certain ways. So what I'll do instead is this then. I'll rewrite that, which I made that blob, as I'll divide it. That's going to go in once with 3 left over. So 1 minus 3 over x plus 1. The reason being, if I've got x minus 2, I can split it into x plus 1 minus 3. Because plus 1 and minus 3 makes minus 2. And if I put them both over the x plus 1, I've got 1 minus that. Rather than just doing the actual division, you can just do that by inspection. Right, so what happens to this then? Well, that simply means as x tends to infinity, I know that, x tends to infinity, y will tend to 1. So I've got a non-vertical asymptote at y equals 1. I'll just highlight these two here. But how does it approach it? That's where this bit's useful. Because as x goes to, let's say, negative infinity, as it tends towards that, what happens to y? Well, it's 1. And if that part's negative, it's going to be minus a negative, so it'll be 1 plus a bit. if x tends to positive infinity, what's going to happen to y? It'll be 1 minus a bit now. That little epsilon is just the difference, which obviously is going to get smaller and smaller and smaller. So drawing my asymptote, y equals 1, as you approach negative infinity, you're going to be 1 plus a bit that's getting smaller and smaller. So it's going to go down like this. As you approach positive infinity, you're going to have 1 minus a bit, so you're going to be approaching from below. So that's the approaches to the asymptotes. Now, turning points, right? So I want dy by dx. Well, I've got that form or that form. That form's actually quite handy because differentiating 1 disappears, and that part's just going to be negative 3 over x plus 1 squared. Just a pattern that you learn about. The square will be the negative of it, plus 3 upon x plus 1 squared. Now what that says is, it's always going upwards. That's never equal to 0. That can't ever be 0 because the top can never be 0. dy by dx is never equal to 0. So there's no turning points. Now I could differentiate it again, but that's already said, that's always going to be increasing. But it could be increasing and switching concavity. So I'll just check my second derivative. So the second derivative is going to be, this time it's going to flip negative. That will be over x plus 1 to the power 3, but I've multiplied by 2, so that's going to be minus 6 over that. Now, for this one here, that can change sign. A square is always positive, so I always have the same sign, but this can flip positive and negative. So I've got two changes of concavity here. This says that if x is less than negative 1, that bottom part will be negative, then the second derivative will be greater than 0, in which case it's concave up. And it says if x is greater than negative 1, then that part there is going to be positive, which makes it negative altogether. So dy by dx squared is going to be less than 0, so it's going to be concave down. And there won't be a point of inflection at x equals negative 1, because x equals negative 1 is forbidden. And that's about it. Now it's just a case of putting it all together. Can we fit it on the page? We'll go up to here and just make a little sketch of it. Put all the information together then. I know it's been a bit crowded, I should have written a bit smaller. Right, so what have I got? We've just got the axis. Y-axis cuts at negative 2. X-axis cuts at 2. Vertical asymptote at negative 1. X equals negative 1. Non-vertical asymptote, horizontal in this case, at y equals 1. Y equals 1. And then just snake it through with all that information. So what's happening? I must be going through these 2 points. How does it approach this one? So it's from this side and it goes underneath the line, so that makes sense. I'll just draw this in red. So it's coming up as an asymptote through those 2 points and creating an asymptote there. That satisfies this part. What happens on the other side? Because I've got these 2 portions here. But I know that it comes from positive infinity and stays above the line, so this part must go like this. But then again, it had to have that, it had to be concave up for that part there. For x is less than negative 1, that had to be concave up and that had to be concave down. So there's the graph there. Maybe that should have been a bit bigger and this should have been smaller over to the side. It's just the way I